Okay. Radioactivity. Actually, if you notice, I'm starting a totally different module with these videos. I'm sure we're gonna have time to go back and finish up electronics and operational amplifiers and so on. But I want to start off these videos with atomic and modern physics. So without further ado, let's go. Definition of radioactivity. Radioactivity is a random process. It's a statistical process, a stochastic process, a spontaneous process. Any one of those terms can be used interchangeably. And this process occurs when an unstable nucleus emits particles. The particles are, if they're particles that are emitted, they're alpha and beta particles. Or they emit energy, gamma radiation, that's energy. The original unstable nucleus is called the parent nucleus, and the resulting more stable nucleus is called the daughter nucleus. That's interesting. I wonder why they didn't call it the sun, but never mind. Poor attempt at humor there. Radioactive decay is observed in several naturally occurring elements, and it can also be observed in artificially produced isotopes of the elements. We're going to talk a lot more about this part, artificially, both actually, naturally occurring and artificially occurring radioactive decay. We're going to revisit that and look more at the chemistry and the physics of that. This first part of radioactivity I want to discuss deals with the mathematics of radioactivity. Okay, for any radioactive process, the rate of decay is directly proportional to the number of parent nuclei present. The rate of decay, first of all, the rate of decay represents a decreasing rate, and that's the reason for the negative right there. So negative dN dt is the rate of decay. That's also referred to as the activity, by the way. And that's proportional to the number of parent nuclei present. If you get rid of the proportionality sign, then you have the constant of proportionality, which is lambda. Lambda is called the decay constant. We're going to get into the definitions a little later. So basically what you set up here is a differential equation. And we all know how to solve differential equations of this nature. You all have done so much calculus and differential equation in your pure maths. You shouldn't have any problems with this. This is actually a separation of variables type differential equation, so no issues. Note this law is based on the assumption that the probability of decay of any atom in the sample is constant. The probability that any one atom will decay is the same as the probability of any other atom decaying. In that equation, in that differential equation, n represents the number of parent nuclei present in the sample at any time t. Number of parent nuclei present in the sample at any time t. Lambda, like I said, is the decay constant. It's directly connected to something else called the half-life. It's also directly connected to the rate of decay. Minus dN dt, the negative dN dt. That's the rate of decay or activity of the radioactive source. All right, I left the space out so that we can actually solve this differential equation to get that end result. So let's go through the process. Let's see if we can solve that equation. I still don't know how to use this thing properly. Okay, so that's my differential equation. I can separate the variables. If I do that, I'll get minus 1 upon n times dn is equal to lambda times dt. Just throw across the dt, bring across the n. And I'll multiply both sides by a negative to put the negative on the other side. So this becomes, and then integrate both sides at the same time. This becomes the integral of 1 upon n times dn is equal to minus the integral of lambda times dt. I want to use limits on my integral. Initially, when time is 0, there is an initial number of parent nuclei present in the sample. I'm going to call that n0. And of course, at any time t, the number of atoms present in the sample is just n. If I were to integrate both sides, shouldn't be an issue here. On the left-hand side, I'll get ln of n, evaluated between n0 and n. On the right-hand side, I'll have minus lambda t, evaluated between 0 and t. Plugging in my limits, ln of n minus ln of n0 is equal to minus lambda t. Plugging in the lower limit of 0, you get 0. Laws of logs will give me ln of n upon n0 being equal to minus lambda t. Change the exponential form, n over n0 is equal to e to the minus lambda t. And then I simply transpose the n0, and I end up with this equation right here, which I'll just pull up. That's the solution to that differential equation. Right there. There it is. That's the solution. That just shows as time goes on, the number of parent nuclei decreases with time. That equation is very similar to the equation or equations you were working with when you were dealing with the RC circuit, the discharge of an RC circuit. You remember? In the discharge of the RC circuit, the current, which is really the rate of flow of charge. Give me a second here. The current, what was it? I was equal to I0 times e to the minus 1 upon RC times t. You remember that? There's a nice problem on one of the past papers that makes the connection between the two. They actually compare the two directly. Where the RC in this equation was the time constant, and the lambda up in this one is the decay constant. So that's an interesting analogy. The two equations look pretty much the same. If I draw a graph for that exponential decay, let me write back the equation here. N is equal to n0 e to the minus lambda t. If I draw the graph, I get an exponential decaying graph. Now, it's very interesting how we can use this graph to calculate something called the half-life. There are other ways to calculate it as well. But if you think about it, if I were to plot this graph, when half the number of initial atoms in the sample have disintegrated, half the number of parent nuclei initially present in the sample have disintegrated. So I start off with n0, and when I get to half of n0, that's there. If I read across and read down, I end up with what's called that time interval from 0 to that point. That's called the half-life. It's the time taken for half the number of radioactive nuclei, the number of the radioactive parent nuclei to disintegrate. If you think about it some more, if I now go down to half of that half, which is a quarter of the initial amount, a quarter n0, I read across and I read down, guess what? An amount of time also equivalent to a half-life expires. Half of that quarter now will give me 1/8. I read across and I read down, another half-life has expired, and so on and so forth. So regardless of the initial number of atoms present in the sample, the half-life would be the time taken for half that number to disintegrate. So this is a very interesting graph that you can use to count the half-life of or to calculate the half-life of a radioactive substance. The activity minus dNdt is measured in becquerels. 1 becquerel is defined as the activity of 1 integration per second, one disintegration per second. That's 1 becquerel. Note the older unit is the Curie, defined after Madame Curie. She had a lot to do with our understanding of radioactivity today. That was defined as an activity of 3.7 times 10 to the 10 disintegrations per second. So that's a big unit. We're going to be using the becquerel. 1 disintegration per second. That's the activity that we're going to be using in those units. Again, down here, I define the half-life of a radioactive element. T subscript a half is the time taken for half the number of paired nuclei in a sample of the substance to disintegrate. We can actually calculate an expression for that half-life from the equation n is equal to n0 e to the minus lambda t. When half the number of elements have disintegrated, the number of elements present is half of the original. So when n is half of the original n0, t would be 1 half-life. If I plug that information, let me do this over. I'll do this part over. If I plug that information into this equation here, there, I will get a half n0 is equal to n0 times e to the minus lambda times t half. When 1 half-life has expired, the number of elements present, number of nuclei, radioactive nuclei present is a half of the original. From this, the n0s will cancel out. That cancels out with that. What's left? A half is equal to e to the minus lambda t, e to the minus lambda t half. I will use my laws of logs and ln both sides. When I do that, I'll get ln over half is equal to minus lambda times t half. Ln over half is negative ln 2. Well, I don't think I have to prove that to you upper sixes. Y'all should know that. Is equal to minus lambda times t half. And divide by minus 1, and we're going to make t half the subject. T half, the half-life. You can use this equation to represent it. It's ln 2 upon lambda. The half-life is ln 2 upon the decay constant. Okay, so that's not too bad. Minus dn dt is equal to lambda n. That's the original differential equation that we were solving. Remember, minus dn dt is used to represent the activity or rate of decay of the radioactive sample. And we're going to give it a separate letter on its own, R for rate of decay. Some books use A for activity. I'm going to use R. So if I replace minus dn dt with R, then the equation, this equation here, becomes this equation. Minus dn dt is equal to lambda n. That becomes R is equal to lambda n. So that's the equation you can use to represent activity. The initial activity or the initial rate of decay, R0, occurs when n is equal to n0. So all we have to do is to plug R equal R0 here and n equal n0, and we end up with this equation. So that's the initial rate of decay in terms of the initial number of parent nuclei present in the sample. Now I ask a question at this point: can we connect the initial activity of a radioactive substance to the activity at any subsequent time in the radioactive process? And the answer is absolutely yes. Now, let me take off some of this and redo it. couple of ways you could have done this. I'm choosing to do it from taking the, I'm going to take the solution to the differential equation, which is n equal n0 e to the minus lambda t. And I will differentiate both sides with respect to t. So this becomes dn dt is equal to, everybody knows how to differentiate that. I don't have to give you pointers there. Minus lambda n0 times e to the minus lambda t. I'm going to multiply both sides by minus 1. And this becomes minus into dn dt is equal to lambda n0 times e to the minus lambda t. And as you would remember from just above, minus dn dt is the activity at any time t, so I'll represent that with r, is equal to, and lambda n0 from right here, it's the initial activity. That would be r0 times e to the minus lambda t, right? This part right there is r0. And here is the equation that relates the activity at any time, activity or rate of decay at any time, to the initial activity or rate of decay. You can clearly see from that equation that as time goes on, the activity decreases, which kind of makes sense. As more of the parent nuclei in a radioactive sample, as they disintegrate, then you have less of them to disintegrate, and the rate at which they're going to disintegrate slows down. And this equation proves it. The initial rate of decay is always the largest, and then the rate at which it decays decreases with time. Okay. Let's go on to the next bit. Finding the number of radioactive parent nuclei remaining in a sample, or the activity of a sample after n half-lives, where n is a positive real number. So the idea behind this, you want to be able to find the number of parent nuclei and also the activity as well. I think I did one for the activity as well. Yes. After a certain number of half-lives, because sometimes you can just look at at a problem and see that they're asking you to do something after 3 half-lives or after 2.5 half-lives or something like that, and you might have, more simplistic expressions or equations that you can use to deal with that. So let's see. I'm going to keep these equations as I have them here. N is equal to n0 e to the minus lambda t, where lambda is equal to ln 2 upon t half, right? Remember, t half was ln 2 upon lambda, so I just changed this up to get that formula. After n half-lives, the time that has elapsed is n times t half. That should make sense. So let's say the half-life of a substance is 10 minutes. Then after 6 half-lives, 6 times 10 would be 60 minutes would have elapsed. Time would be 60. So that's kind of what I'm capturing here. After n half-lives, the time that has elapsed is n times the value for the half-life. Now what we're going to do, we're going to plug in n t half for the value of t. If we did that, we're going to get n is equal to n0 e to the minus. For lambda, I'm plugging in ln 2 upon t half. And for t, I'm plugging in n times t half. Well, guess what? The t halves cancel out. What's left? N is equal to n0 e to the minus n ln 2. Humpty buddy. N0. Lord have mercy. Finally. All right, yes. If we use a little indices, we're going to throw the minus n on top. We get that's equal to e to the minus ln 2. Oops, I messed that up. That's equal to e to the power ln 2 to the power minus n. And you should know from your logs that e to the ln of k is k. So therefore, e to the ln of 2 to the minus n is 2 to the minus n. And therefore, I'm forgetting my n0 in front there. And therefore, n is equal to n0 times 2 to the minus n. There. Doesn't depend on time at all. A similar analysis, you will go through that one if you want to. But a similar analysis will give you, if we start off with, for the rate of decay, r is equal to r0, e to the minus lambda t. Guess what I end up with? You'll end up with an equation that says, if I can get this thing to work, that would be nice. You'll end up with an equation that says r is equal to r0 times 2 to the power minus n. There. So, we have a lot of nice equations that we can use to our advantage, and I've summarized them all at the bottom here. And they're all quotable. You can quote them and use them to your advantage. Let's start off. I'll just read them back. Starting off with the original differential equation, minus dn dt is equal to lambda n. The next one gives r, the activity, is equal to lambda n. Activity in terms of the number of parent nuclei present at any time. And then the initial activity, R0, is lambda n0, where n0 is the initial number of parent nuclei initially present. And the number of parent nuclei present at any time is equal to n0 e to the minus lambda t. Half-life and the decay constant are related by the equation T half is ln 2 upon lambda. The rate of decay at any time t is related to the original rate of decay by the equation r is equal to r0 e to the minus lambda t. And then we have those two last equations that I derived there. N is equal to n0 times 2 to the minus n, and r is equal to r0 times 2 to the minus n. The first one gives the number of parent nuclei present in a sample after n half-lives. Note, n doesn't have to be a whole number. It could be 2.75 half-lives or 3.975 half-lives. Or it could be a whole number, but it doesn't have to be a whole number. Right? N is the number of half-lives, where n is a member of the set of positive real numbers. And you're given it in terms of the initial number of parent nuclei present in the sample. Similarly, the last one, r is equal to r0 times 2 to the minus n. That gives the activity of a radioactive sample after n half-lives. Again, n does not necessarily have to be a whole number. And you're given that activity in terms of the initial activity. So whatever set of problems that they want you to solve will come from this set of equations, man. You got it all right there, summarized for you. I'm gonna do, well, I've already done them and they're in here. So let's just discuss. This first problem came from the Mooncaster text, page 893, G86. Discuss the assumptions on which the law of radioactive decay is based. My response: assumptions are probability of decay is a constant. And secondly, I should have extended that. The probability of decay of any one atom, of any atom. Sure. Is a constant. And the rate of decay is directly proportional to the number of paired nuclei present. That directly gave rise to the differential equation that we solved. Second part of the question is asking what is meant by the term half-life of a radioactive substance. Half-life, that's the time it takes for half the number of radioactive paired nuclei in a sample to disintegrate. Next part of the question says, a small volume of solution which contains a radioactive isotope of sodium has an activity of 1200 disintegrations per minute when it was injected into the bloodstream of a patient. Okay. After 30 hours, the activity of 1.0 centimeters cube of the blood was found to be 0.50 disintegrations per minute. If the half-life of the sodium isotope is 15 hours, estimate the volume of blood in the patient. I kind of like this problem. What I did a full conversion. I realized afterwards I didn't have to. I'll explain what I mean. I converted everything to standard units. So for the radioactive isotope, they gave the half-life as 15 hours. That is 54,000 seconds. The initial rate of decay, they gave that as 12,000 disintegrations per minute. Let me make sure. It's 12,000 disintegrations per minute. I converted that to disintegrations per second, which is a becquerel. So that's standard units as well. After 30 hours, right, effectively they gave the radioactive substance to distribute itself throughout the entire bloodstream. I mean, after 30 hours with the heart pumping and everything else, you wouldn't expect the radioactive substance that was injected, wherever it was injected, let's say it was injected into the arm, it's not going to stay in that spot. That radioactive substance is going to distribute itself throughout the bloodstream. So when they just draw 1 centimeter cube of the patient's blood, that will be the activity in that 1 centimeter cube after the 30 hours. What you'll have to do is to multiply 1 centimeters cube by the V centimeters cube, which is the volume of the patient's blood, and that will give you the activity for the entire bloodstream after 30 hours. So let's see what I did here. After 30 hours, I converted that to seconds as well. 1 centimeter cube of the patient's blood has an activity of 0.5 disintegrations per minute. I automatically converted that to disintegrations per second, 30 becquerels. And then here's the logic. You have 1 centimeter cube has an activity of 30 becquerels. Therefore, if V is the volume of the patient's blood in centimeters cube, then V times that 1 centimeter cube, V centimeters cube would have an activity of 30 V becquerels. That kind of should make sense. If 1 centimeters cube gives you 30 becquerels, then V centimeters cube will give you 30 V becquerels. So I've summarized the information here now. Up here, I just extended everything. The initial activity is 720,000 becquerels. After 30 hours, which is a time of 108,000 seconds, the activity was 30 V becquerels. And the half-life, which was 15 hours, ended up being 54,000 seconds. So all that stuff above was just so that I can get this bit of information right there. That's what I need. Now I'm going to take that information and plug it into this equation. R is equal to R0. So in other words, the equation relating the initial rate of decay to the rate of decay after 30 hours. They didn't give me the decay constant. They gave me the half-life. So in this equation, I'm going to substitute ln 2 upon t half for the decay constant. So r is equal to r0 e to the minus ln 2 upon t half times t. And I simply plug everything in. For the rate of decay after 30 hours, that's 30V right there. Initial rate of decay is 720,000 becquerels. That's there. And then e to the minus ln 2 upon t half. T half is 50. Ooh, what happened? I don't know what happened. I hope I can continue from where I left off. Something strange happened. Maybe I touched the wrong button or something. Anyway, let's hope it continues because it looks like I see that red button is still there. So hopefully I'm still on this video. Yeah, so R is equal to, where was I? If I plug in, I'm plugging in 30V for the rate of decay after 30 hours. 30V becquerels. I'm plugging in 720,000 becquerels for the initial rate of decay. That's where I want to be. Yes, right there. For the lambda, I'm plugging in minus ln 2 upon t half, which is minus ln 2 upon 54,000. And for t half itself, sorry, for time, is 108,000. If you look at that, the only unknown in there is V, from which I can calculate V to be 6,000 centimeters cubed of blood. That's an interesting result. Alternatively, I could have made my life a little simpler in many respects. Check this out. I could have solved this same problem as follows. But I wanted to show both ways. If I use the equation relating the rate of decay at time t to the initial rate of decay times the number of half-lives, if you look, the half-life of this radioactive substance is 15 hours, and you were checking on the activity after 30 hours. Where was that? Yes, after 30 hours. So after 30 hours have elapsed, that represents 2 half-lives. That's the first thing. The second thing is I did not have to convert necessarily to becquerels. I could have left the units in disintegrations per second. For example, 1 centimeter cube represents 0.50 disintegrations per second, per minute. Therefore, V centimeters cube is 0.5 V disintegrations per minute. The original rate of decay, R0, they gave that as, what was the number they gave? As 12,000 disintegrations per minute. I could have left that in disintegrations per minute as well. 12,000 disintegrations. Because you see, if I put disintegrations per minute on both sides, then that doesn't affect anything. Keeping in mind, V is still in centimeters cubed. So if I plug in, I'll get R, which is 0.5 V, is equal to R0, which is 12,000 times 2 to the minus 2. The number of half-lives is 2 half-lives. So that's 2 to the minus 2. So therefore, V is equal to, 0.5 is a half. If I carry the half on the other side, it becomes 2 times 12,000, and 2 to the minus 2 is a quarter. Voila. 2 times a quarter is a half of 12,000 is 6,000 centimeters cubed. So I could have just worked on based on the number of half-lives present, and that would have given me the same result, which I think is pretty cool. Okay. Now, just for your information, FYI, the average volume of blood in a female is 9 pints. The average average volume of blood in a male is 12 pints. And the 6,000 centimeters cubed that we just calculated up there is approximately 12.7 pints. So I think that was pretty good calculation. Okay, I also went through another problem. This one here. This one is taken from a past paper. Physics Unit 2. This is 2012, the year 2012, and it's number 6. So let's run this one as well. Radon has the nuclear formula, radon 22686. State the number of protons, neutrons, and electrons that are in a neutral atom. All right. I didn't go through any of this, but this should be whoever is doing chemistry should be okay with stuff like this. The proton number is the number at the bottom. That's the 86. The number of neutrons, well, the number on top, the 226, that represents the nucleon number, the number of protons and neutrons together. So if the number of protons is 86, if you subtract that from the 226, then 140 represents the number of neutrons. And in an electrically neutral atom, the number of electrons must match the number of protons. Electrons are negatively charged, the protons are positively charged, and they have the same amount of charge. So therefore, it's 1.602 times 10 to the minus 19 coulombs. So the number of protons must match the number of electrons for you to have an electrically neutral atom. The next thing they were asking for is explain what is meant by an isotope. Okay, again, these are things, general knowledge things that you would have picked up along the way. I'm going to go through it in a separate tutorial though. An isotope is a variation of an element having the same proton number but a different neutron number. Same number of protons but a different number of neutrons. Carbon is a good example. You have carbon 11, carbon 12, carbon 14. But each one of those carbons has six protons. So carbon 11 would be written as C11,6. Carbon 12 would be written as C12,6. Carbon 14 would be C14,6. That simply means you have the same number of protons, but a larger number of neutrons in carbon 12 and carbon 14 that you have in carbon 11. They also want you to define half-life and radioactive decay, the decay constant. Half-life, we defined it before, but I defined it again in this example. The half-life of radioactive nucleus is the time taken for half of the parent nuclei in a sample of the element to decay. The decay constant of a radioactive substance is a measure of the activity or rate of decay. The decay constant is also directly related to the half-life. Right? The longer the decay constant, the shorter the half-life. And I've shown the equation right there. I think they asked for the equation as well. All right, let's keep going. A radioactive sample contains 3.50 micrograms of pure carbon-11, which has a half-life of 20.4 minutes. Okay. Determine the number of nuclei in the sample when time is 0. Again, this is some simple stuff I'm sure you've seen in your chemistry before, relating to, or somewhere along the line. Even you probably would have done CSEC chemistry, I'm sure. 3.5 micrograms represents 3.5 times 10 to the minus 6 grams. Half-life is 20.4 minutes. I'm going to convert that to seconds. Carbon 11. The 11 means that there are 11 grams in 1 mole of carbon. And any 1 mole, we know Avogadro's number, 1 mole of a substance contains 6.02 times 10 to the 23 atoms. So 11 grams represents 6.02 times 10 to the 23 atoms. So therefore, I simply need to know what 3.5 micrograms represents in terms of number of atoms. So you divide by 11 to figure out for 1 gram, and then you multiply that by 3.5 times 10 to the minus 6. So when you crunch all of that, the number of atoms in a 3.5 microgram sample is 1.92 times 10 to the 17 atoms, as shown there. So the calculation there is not that difficult. The next thing they wanted was the decay constant. Okay, well, that's pretty straightforward as well. It's ln 2 upon t half. Ln 2 upon the half-life, you have to put that in seconds if you want to have the units of lambda in standard units. That would be per second. So that's the calculation there. Ln 2 upon 1224 gives me 5.66 times 10 to the minus 4 per second. The next thing they wanted, I think, was the initial rate of decay, or the activity or rate of decay in the sample at time t equals 0. So that's the initial rate of decay. The initial rate of decay is given by lambda n 0, one of the equations I took from the summarized list I have above. When you multiply the two, you get the initial rate of decay as 1.09 times 10 to the 14 becquerels. By the way, you should check all these numbers. I mean, y'all know how skilled I am at using a calculator, right? So please confirm these numbers. And if there is an error somewhere, please let me know. I think I'm right, though. All right, what else? And then the last thing they wanted was the activity after 8 hours. Well, we'll simply relate the activity after 8 hours to the initial activity. We'll convert the 8 hours to seconds, and we'll use this equation right there. R is equal to R0 e to the minus lambda t. We already calculated lambda, so it's just plug and chug. R is equal to initial rate of decay, which is 1.09 times 10 to the 14, e to the minus lambda, minus 5.66 times 10 to the minus 4, times t. And 8 hours is 28,800 seconds. Crank the handle on that, and you should get R is equal to 9.08 times 10 to the 6 becquerel. So after 8 hours, the activity gone down. Activity initially was 1.09 times 10 to the 14, and after 8 hours is 9.08 times 10 to the 6. So, but 8 hours is probably 20 something half-lives. So that number kind of makes sense. All right, that is this video, and you obviously notice you have a nice worksheet here. You're welcome. Questions 52b, and this is from the Muncaster text, obviously. Page 813, you got the numbers there, and then page 893, you got the numbers there. I think I did this one, G86 already. So, we got one down. All right, that's it for this one. The next video I'm going to do on radioactivity will be, I'll talk specifically about alpha, beta, and gamma radiation, and, you know, the properties, distance that the particles travel in air, and so on and so forth, etc., etc. And then there are several other parts to this. So you're going to see several other videos coming up. We also got to talk about the photoelectric effect, and yeah, a bunch of stuff coming up. So that's it for this first video. All right, I'm out.